this notebook covers just a basic imaging mode simulation. And so I just want to point out, we'll get started with imports and convenience functions. We're going to spend a bit of time on these source catalogs just because there are a number of different ways to create them. And then we will use those and create the input YAML files, simulate the data. And then if there's time, there is a way to call the simulation steps independently if you wanted to, for example, only make the seed images. And then some extra material on running with multiple exposures or simulating a deep field, which takes a little bit longer. So in terms of getting started, as I mentioned, there are a few environment variables that you need to set for Mirage to work. In this case, on the platform, they're not as important. I think these are going to be set for everyone by default. But in terms of running them on the platform, these are what you need. If you're running locally, you need to use something else. You need to have your own CRDS cache location, and you need to have the reference files, the Mirage reference files somewhere. So let's get started by setting those, importing those. And then we've got just some basic imports here. From Mirage, we're going to import the imaging simulator, which is the full wrapper script. Some functions for creating source catalogs. And then these are the 3 steps that the imaging simulator wraps around, and then the YAML generator. So we'll start by defining the XML pointing files from an example APT program. And so those you can download. And maybe while that's downloading, I will bring APT in here and just show you. So it's a very basic program that I created. We've got 2 targets, one called Starfield and one called Extragalactic. And we've got 2 observations. Each observation uses one of these targets. And so just keep this in mind as we run through the YAML generator in the simulator, you'll see, because we'll refer back to these targets a couple of times. So we'll define a convenience function for showing the data later on in the notebook. Okay, so now we'll work on creating some source catalogs. So we've got 3 types of source catalogs to work on here for this one. So the point sources, the galaxies, and the extended sources. And yet one important note on these catalogs, you'll see below as we look at them, there's an index column. And it's important that even if you're using multiple catalogs, every target needs to have its own unique index number. And that's because Mirage will create a segmentation map as part of the output. And so you need to, each object needs to have its own independent number to use in that segmentation map. So maybe the quickest way, if you don't have your own catalog already, maybe the quickest way to create one is to use these for proposal or get all catalogs functions. And so what these functions will do is go in and for point sources, they will query the 2MASS Gaia and WISE databases and return a list of stars in the areas on the sky that you are looking at. There's also an option to use as input and output of this Besançon galaxy model. And the reason that's there is because these databases all cut off at a magnitude of v equals 16 or so. So if you want dimmer point sources, this is the way to do it. So this will get the density of stars on the sky about right for where you're looking, but they won't be real stars. It's just a statistical model of the stars. And so what a lot of these functions will do, though, is it will take the inputs from these various sources, and it will then, you can supply the JWST filters that you're interested in observing through, and Mirage will interpolate to find magnitudes of all the sources through those passbands. So in this notebook, I'm going to skip the Besançon query because that's a multi-step kind of offline process. It takes a while. So there is in the example notebook on the repository, it shows how to do that. So let's start with this for proposal function. Oh, right. So I covered the point sources. So these functions will also then have the option of creating a catalog of extragalactic sources. And so in this case, it's sort of similar to the Besançon example with the point sources, where Mirage will query the 3D-HST catalog and come back with a representative sample of galaxies in this catalog. So there won't be actual galaxies on the sky where you're looking, but there'll be just a representative sample. So let's define the output catalog, and let's just start this running because it takes a second. So what this is going to do for proposal, it is going to take the APT XML file and pointing file, and we're telling it to create a point source and an extragalactic catalog. We're skipping the Besançon, and we're going to save the catalogs. And so what this is going to output are point source and galaxy catalogs that correspond to each of the two targets that I showed from the APT file. So here you can see it searching the various databases. Okay, and so now it's finished. Let me So you can see the output here is we have a large tuple of things. So let's look at what's included. So there are 2 point source catalogs, which makes sense because we have 2 targets in the APT file. And these are the output catalog names. In general, it will name the catalogs with 001 and 002. These correspond to the observation numbers in the APT file. But it also supplies a mapping, so you can see that observation 1 corresponds to this catalog, and observation 2 is this other one. And so let's just take a quick look what the source catalog looks like. So you can see there's an index column, and we've got RA and DEC, and then we've got magnitudes through these 2 filters, and these are the 2 filters that are specified in the APT file here, 150W and 444W. And so this catalog covers the area on the sky associated with the first target in APT. And then the other catalog covers the other source in APT. And then similarly for the galaxies, you've got a mapping here. You've got galaxy catalogs for each associated with each target. And then again, if you look at this one of these galaxy catalogs, here's the index. In this case, the function knew already about the point source catalog and that it had 15 sources in it. So it started the galaxy catalog at number 16. And again, we've got RA-DEC, position angle, Sirsic index, ellipticity, radius, and magnitudes. And in this case, this catalog is quite large. It's almost 2,200 objects. So that's maybe the quickest way to create a catalog if you don't have anything to start with ahead of time for your proposal. So it'll just use the proposal itself. If you, for whatever reason, want to create a catalog, you want to have a little more control and create a catalog for a given area of sky and cover a given size, given field of view, you can use this getAllCatalogs function. So this will do more or less the same thing, except in this case, you have control over the size of the catalog. But it's still going to go and it will query Gaia 2mass and Ys. And so this is going to create just the point source catalog. So similar to what we saw before. And then you can save it using the save method. And then similarly for the background galaxies, if you want to create a catalog that covers a specific area on the sky, specify RA-Dec of the center of the catalog and then the width. So again, all right, and so in this case, I should point out, I use the starting index input so I can specify the beginning of the index numbers. So that's how you can control, if you're making things manually, and make sure that the index numbers don't overlap between catalogs. Save it. If you do have your own catalog and you want to convert it into a Mirage formatted catalog that it understands, you can do that. There's a convenience function for that. So in this case, we're just going to build a little catalog here, and you can see, so here we've got just a catalog with RA-Dec and then VJHK. And so let's save that. So if you're starting with that, then what you can do is you have to manually specify the instruments and filters that you're interested in converting to. And then an output name. And then you can run this Johnson catalog to Mirage catalog function. And you supply the catalog, the filters you want. The RA-Dec, that's just the name of the columns here in your input catalog that contain RA-Dec. And so what that will do is interpolate over these magnitudes in order to create magnitudes through the filters that you requested. So this catalog is now ready to go right into Mirage. And then finally, the final way to create a catalog, which these are the catalogs we'll use for the simulation in this notebook. This is going to be creating something by hand just from scratch. So here we've got a range of RA-Decs. We're going to create a catalog of 450 stars. We're going to use random. We're going to randomize the RA-Decs over the field of view. We're going to use some random magnitudes. And then what we'll do is we will use the point source catalog class, excuse me. And so what that call does is creates kind of the skeleton of the catalog. That includes the RA-Dec. And then one at a time for each filter you're interested in, you can add the magnitudes, add the magnitude columns. So here we generated the magnitude values, and here we're adding them to the catalog, one filter at a time. So you can save that. And then here we have our catalog with the 3 filters we requested. And then similarly for the galaxies, again, we'll create just a random 20 galaxies with random RA-Decs, and then also all the appropriate radius ellipticity that we need. Let's manually add this one specific galaxy so that we can easily zoom in on it later in the output. And around here. So the next step then, once you have all that in place, is to use the Galaxy Catalog class to create the skeleton of it, create some magnitude values, and then just like before, one filter at a time, we'll add the magnitude columns to the output. So we'll save that. And here's our catalog. And then the final type of catalog here that I mentioned before is this extended source catalog. So this is if you have a stamp image, a FITS file of your target, if it's got some complex morphology and you want to add that. So in this case, I have an example that we can download. And then just to show what it looks like here, we can open it. We'll use our convenience function to take a look at it. Okay, so we've got some source with some morphology that's more complex than you can do with just a 2D surstick. And so we want to add this to our scene. So first we specify the ARIA index and the file name, and then the position angle, because Mirage can rotate the stamp if you want it to. And then what we'll do is we'll call the extended catalog class to create that catalog. We'll create some magnitude values to use, and we'll, again, one at a time, we'll add magnitude columns to the catalog. And then, so here's our one-line extended source catalog. And you can see in this case, I made the starting index very large just to be sure that it wasn't overlapping. And then we save that. So at this point, we've got all of our catalogs that we're going to use. We're going to use these manually generated ones. So we want to move on to generate the input YAML files. So in addition to the catalogs, there are a number of optional user inputs. There are more details about all of these on the documentation page online. Well, I'll kind of breeze through them here, but there are more complex options that you can see there. So for the catalogs, those have to go in a dictionary. In general, if you used like the for proposal function, you can just directly use the mappings and create this dictionary. So I should point out first, this dictionary has the keys. The main keys are the target names from your APT file. And then for each one of those, you have a dictionary that includes the different types of catalogs to use for that simulation, for that target. So in general, you can just use the point source mapping or the galaxy mapping. In our case, we're going to use these manually generated catalogs. So you can see here, they're a little bit different. So once you have that, so in terms of other optional inputs, pipeline reference files, in general, it's probably best to keep this set to the string CRDS. What this controls is where Mirage looks for the CRDS reference files. So these are the official JWST reference files that are used by the calibration pipeline. Mirage also uses some of them in the creation of the data. So it's generally best to just set this to CRDS, and then Mirage will go to CRDS and get the official best copies of everything. But if you wanted to override it with your own reference files, or if you have different reference files, you can do that here. And there are details in the documentation for that. Cosmic rays. Mirage uses a cosmic ray library that it selects cosmic rays from and adds them to the scene at some rate. So by changing the library or changing the scale, you can change the rate that the cosmic rays are put down onto your simulated image. In terms of background, Mirage follows the ETC conventions where you can do low, medium, or high, and the definitions are the same. You can specify low, medium, or high for the entire proposal, or if you have different observations, you can specify the background per observation. And then finally, another option, which we're not going to use here, but which can be used, there will be when we call the YAML generator, there's this date obs for background option. And if you set that to true, then Mirage will ignore this, and it will use the observation date that you specify, and it will go look up the background value for your pointing location on that date and use that. Similarly, you can specify the roll angle of the telescope. You can do that for the entire proposal or per observation. And then same also with the observation date. If this date obs for background is turned off, then the date is only used to, it goes right into the header of the output files and it's not really used for anything else. But if this is true, then it will be used to generate the background. In terms of optical ghosts, if you're doing MIRISim simulations for a subset of the MIRISim filters, the MIRISim team has characterized ghosts well enough that Mirage can add them. In this case, for this example, we're doing near cam observations, so these are going to be ignored. So once you have these various optional inputs set, you can specify the output directory where you want the YAML files to be, as well as the output directory where you want the simulated data to eventually end up. And you can specify the output type. So this is what I was speaking about before, where raw is equivalent to the level 1B files, and then linear are the linearized ramps. So once you have all of that defined, you can run the YAML generator using this sim input class, and you provide everything. So you provide the APT, XML pointing files, all of these optional inputs we just went over, output directories, data types, and you create the input files. So you can see it will step through, it will get information on the targets out of the APT file, and then it will step through the observations, and it will look at dithers and mosaics and the number of detectors that you're using and subarrays, and it will create YAML files for everything. And so you can see if you go down to the bottom here, you can see for observation 1, we created 30 files. For observation 2, it created 15. So you've got 45 YAML files in total. And so now that we have these, okay, so here's a list of our YAML files. Now that we have these, let's actually look at one and see what is inside. So we'll just choose one. And so it's pretty similar, I think, to the MIRISim files that we were looking at earlier, except Mirage does everything in a single YAML file. So there you can specify, it specifies the instrument, the mode that you're simulating, the read pattern, the number of groups of your integration, the number of groups in the integration, number of integrations in the exposure, the array name, which is essentially the subarray that's going to be used, filters, and then it mentions here are the reference files that we were talking about. There are some various files that define where the subarrays sit and what the crosstalk looks like. Cosmic ray libraries. And then here in the sim signals section, you have your point source catalog, and then also the location of the pre-computed PSF library, which is where Mirage will get the PSFs from to add to the scene. The Galaxy catalog, the extended catalog. These are other types of catalogs that we didn't specify, so those are all set to none. And then down here, we've got the telescope pointing. And so this, I should point out, is the RAN deck of the reference location of the subarray, which is usually the center of the subarray for this particular exposure. And then in the output, we've got the output file name and then where it's going to go. And then there's a whole bunch of information in here that will just go into the header. This is all pulled out of the APT file. And so now that we have the YAML files, now we can actually run the simulator itself and create some data. And so in this case, as I mentioned, Mirage is, I generally think of it as these 3 steps: the seed image, the dark current preparation, and then the combination of those 2. So in this case, we're just going to call the imaging simulator, which is a wrapper around those 3 steps. And so just to point out a few highlights, it will tell you where the log is. And then once it completes this log, will be moved into a log subdirectory. It tells you the YAML file it's working with. Once we get into this step here, so the JWST package kind of hijacks the logging a bit, so every entry is in here twice, which makes it a little difficult to read, but you can see it's going into CRDS and it's looking for all of the reference files that it needs. And so if you have them locally, it will be quick. If you don't have them locally, it will download them. I believe everything should be downloaded already onto the platform, so hopefully no one has to download those. And so, just took me to the bottom. Anyway, so it'll create the seed image. I just wanted to point out, so it'll talk about the readout pattern with the number of groups and integrations. Here it's moved on to the dark current file and it's reordering it to the 1 integration and 8 groups, which is what we specified. And then it will go through and combine everything. And so if we go down to the bottom, not quite done yet. So the final step is this unlinearization process, because Raj is starting from the seed image, which is a rate image. And the dark current exposure in general is a linear ramp. So it combines the two, and then the last step it does is it basically runs the linearity correction in reverse to bring the data back to a raw state, to the uncal state. So then it says imaging simulator complete. And so now we can have a quick look. First we'll look at the seed image. So here, the scaling is such just to make things a little more visible, but we've kind of blown things away. But here, this is, we'll see later, this is our extended source. And then we've got some galaxies and some point sources. So if we zoom in on just one part of this, here's the galaxy that we added manually, independently, just to show that we've got this very elliptical galaxy sitting here. And then if we zoom in on the area where we know the extended source is sitting, there's our extended source from the stamp file, stamp image that we have. And then we also have the raw file itself, the file that can go into the pipeline. So we can open that up and look. Here's the format. So you can see the format, the file format here matches the uncal file format for real JWST data. The science data are in the science extension, 2K by 2K by 8 groups by 1 integration. Grab the raw data and so here we're going to look at, this is the last group of the 0th integration. And so here you can see all of the detector effects that dominate the raw files. So we've got the 4 amplifiers here, these 4 vertical stripes. There are bias signal differences with this picture frame effect. So it's much harder to see the actual sources. So one way to kind of clean this up is to look at a difference image. If we look at the last group minus the first group, and so here we're back to something that looks pretty close to our seed image. And then just quickly, I did also output the linearized ramp. So looking at that wouldn't show us anything new, but I just wanted to show the difference between the linearized ramp and the raw ramp. So this is for a given pixel looking up the ramp, looking at the signal up the ramp in the linearized ramp and the raw ramp. And you can see there's a big difference. The raw one starts at a much higher level. That's because the bias level is still included in the data, whereas it's not in the linearized data. And if we plot those two, so we'll make some times to plot against. If we plot those two here, you can see, so the red is the linearized ramp, The blue is in the raw ramp. And the dashed black line is a straight line that's based on the slope between the first two blue points. So you can see that as you get closer and closer to full well, the raw file, the nonlinearity becomes more and more apparent as you get up the ramp. So maybe I will skip this next section. So the next section, this section was just to run the 3 steps of Mirage independently. The outputs are all the same. I guess the only thing that we miss out on here, so these other output products. So this is one of the intermediate outputs that I mentioned earlier. So this is a list of the sources that are only present on the detector in the simulated image. And so it's got just the RA-DEC, it's got the pixel location of the source, the magnitude, and then what counts per second and counts per frame that translates into. And then the same is true of the galaxy and the extended source. So you can see in this case, we've only got 4 galaxies that ended up on the detector. And here, oops, here's our extended source. And then in addition, there's a cosmic ray table. So this shows for the XY location of each cosmic ray along with the group number or frame number where it was added. And so that's good. That's helpful if you want to check and see how well your cosmic ray rejection scheme is going. And then, as I mentioned before, everything is saved into a log file. This is going to be identical to what we saw on the screen up above as it was running the imaging simulator. Skip down there. Let's see, I will skip these. These are the other 2 steps, so preparing the dark current and then combining those 2. And then just for fun, so this section we've got 5 different YAML files. I'm not going to run this, so this will create the seed images for each of these 5 files. But these 5 files, I should point out, they all are for the same exposure for all 5 of NIRCam's B module detectors. So instead of running this cell, you can download the seed images here. And then just to show that, download them, read them in, and then we can look at them. And then this is just to show that it's relatively straightforward with Mirage to simulate the shortwave and longwave channel 5 detectors, and that they share the same field of view. So here we have the shortwave. These are the 4 detectors, B1, 2, 3, and 4. And then this is the longwave detector, B5. And it's a little bit hard to see with the size of these figures, but if you kind of flip back and forth, you can convince yourself that you are looking at the same area on the sky. This I will skip for now. So this is just simulating a deep field exposure. So the scene has a lot of galaxies in it, which takes Mirage a little bit longer since they're so large. But you can feel free to run this. Oh, right. I did actually put in you can download this. So just to show what it would look like. So here's our seed image. And in this case, we've got a bunch of galaxies in here. There are a handful of point sources as well. We zoom in on just one area here, just to show a representative area. So if you were doing a deep field simulation, you could read it that way. And then, so once you have your raw files, you can run them through the pipeline. There's another link to that pipeline documentation here. And that's it.